Hello to everyone. Welcome to this webinar series. I'm David Lumbreras from the Universitat Politècnica of Catalonia, and with me is Sergio Busquets from the same university. This webinar series is just a webinar series from several European projects that we are working on the advancement, on the improvement of the electrical mobility. And particularly this first webinar is about the power electronics in this electrical mobility. Today we have two webinars. The first is from the RHODaS project and the second one is from the SCAPE project. And both are focusing or focused on the different parts of this and different approaches to this to the power electronics in electrical vehicles. Both projects work with the wide backup power converters, with multi-level converters, and with modular and scalable designs. So let's start with the first presentation, which is about the RHODaS project. And I have to say that each presentation will last for 20 minutes, more or less. And at the end of both presentations, it will be a Q&A session. So let's start with the RHODaS project. Okay. So this webinar of the RHODaS project is called Design and Evaluation of a Hybrid Wideband T-type Converter for Heavy-Duty Electric Transport Applications. And here we have the outline of this webinar. First, I will introduce you about the status of the power converter in electric transport, about a little bit about wideband gap semiconductors, and about the hybrid power converter concept design, which is a design that mixes different semiconductor topologies. Then we will see some aspects about the design of this power converter. And then we will present some experimental results. So let's start with the introduction. So nowadays, the electrical mobility is growing. There are tons of manufacturers investing on this kind of mobility. And the standard thing in electrical cars or electrical trucks is to use two-level SiC-based converters, power converters based on silicon carbide, which is a new technology that we will talk about it later. These power converters are more efficient than traditional power converters based on traditional technologies like the silicon, but they have some problems and they can be further improved. So one of the main problems of this kind of power converter is the common mode voltage that generates the operation of the power converters. So there is a trend in the research and also in industry, which is about to researching for new power converter technologies and for advanced modulations to solve these kind of problems. In this project, in the RHODaS project, we proposed a T-type power converter because it's a power converter that you can see on the screen. And it uses 4 transistors, 2 transistors connected to the midpoint of the DC bus and 2 other transistors connected to the upper side and to the lower side of the DC bus. This topology uses fewer components than other multi-level component topologies, like the neutral point converters or like the flame capacitor converters. So it should be cheaper. And it has gained interest on the industry. And moreover, this topology has a particularity that if we don't use, if there is a failure on the transistors connected to the midpoint, it can continue the operation using only the superior, the higher and the lower transistors. So it has some fault tolerance that it's really useful in the electrical mobility. because if there is a failure during the operation of the vehicle, we can just replace we can continue the operation without replacing the affected branch or the power converter. So as I said before, these power converters use the wide bandgap semiconductors. Wide bandgap until a few years ago, the standard on the industry was using silicon transistors, but the silicon is already the properties of the silicon are well known, and it's difficult to improve them. So there are new materials that have superior properties compared with the silicon devices. So the main technologies are the silicon carbide, SiC, and the gallium nitride, GaN. These transistors are able to operate at high switching frequencies with low losses. And there are, especially the gallium nitride is smaller than the silicon. So these semiconductors allow us to manufacture high density power converters. Power converters which operate with higher powers, with higher voltage, and in less space. Particularly, the silicon carbide is preferred for high voltage and for high power applications because they can withstand high voltages, about more than 1000 volts, and their thermal conductivity is really, really good, as you can see on the screen. However, the gallium nitride can withstand lower voltage. I think that more or less the maximum transistors, commercially available transistors, can withstand about 600 volts, and the current on these transistors is limited. And they have also another problem, which is their low thermal conductivity. Is even lower than silicon, than the thermal conductivity of silicon. So extract the heat from this transistor is difficult, and the design of the thermal management system is more complicated. We will talk especially about the thermal management system in other session of these webinars, but not today. But the gallium nitride has a very interesting property, which is their high efficiency. It can work with really, really, really high switching frequencies, and the losses are really, really low. So it's despite the complication of this, including these transistors in the design, is worth including them. So here we have the power converter developed on the RHODaS project. It's a hybrid power converter. In this case, as I said before, this is a T-type converter. So we have the higher and the lower transistors, and we have some transistors connected to the midpoint of the DC bus. To generate, this is a 3-level converter, so we can generate 3 voltage levels at the output: the positive voltage, the negative voltage, and the 0 voltage. The point here is that we used gallium nitride to connect the phase with the midpoint of the DC bus, because these transistors, the transistors which are in the midpoint, only withstand half of the DC bus voltage. So, and the superior, the higher and the lower transistors withstand all the DC bus voltage. So we can use we can use gallium nitride transistors to connect to the midpoint, because although they can withstand less voltage, they can operate in this position because they withstand less voltage than the silicon transistors, than the silicon carbide transistors. So this allows us to improve the efficiency of the T-type converter using the gallium nitride on this position, especially the switching losses. However, the design is more complex, since for now there are no hybrid power modules, and we have to mix SiC power modules and discrete GaNs, or only discrete components. Moreover, the GaN has another problem, and as I said before, which is the current that they can withstand. So when we talk about the heavy duty mobility, we talk about trucks, the powers of the power converter, the power rating is really high and the currents are really high. So it may be necessary to put several GaN transistors in parallel to work with higher powers, which is what we have done in this project. We have developed a high power converter that has three GaN branches in parallel to withstand these high currents. So let's talk with more detail about the power converter design and implementation. And first, we will talk about the design bottlenecks. The main bottleneck of this design is the gallium nitride. For the problems that I said before, the low thermal conductivity, their low current capability, and also about because they are really sensitive to the noise spikes, especially on the rate. So we have to perform a very good designs when we work with gallium nitride, because otherwise they can be noise on the circuit. The converter cannot work well, or even can explode. So let's talk with more detail about these topics. First of all, we have the thermal dissipation, as I said before. The gallium nitride is commercialized in really small packages, and this, with the addition of the low thermal conductivity, makes really difficult to extract the heat from these transistors. So we have to use advanced thermal management systems. For instance, we can use thermal interface materials based on graphene to extract the heat better. We can use also the liquid cooling and so on. But this is a bottleneck of the design, and we have to design always thinking about how we will extract the heat from the GaN transistors. This is a really critical point. Then we have the gate driver and also the gate for the GaN transistors. Another problem with of the GaN transistors is that they turn on with a very low voltage, around 1 volt. So if we have a voltage spike on the gate, it's really easy that the GaN is turned on and we can cause a short circuit. There are many ways to avoid this behavior, and we will talk about this later, but it can be done using appropriate drivers, and also optimizing the layout and also the design of the PCB. And then we have the current handling limitations. The GaN transistors of this voltage level, for now commercially available, they can only withstand about 60 amperes. So if we want to operate with higher powers, with higher currents, we need to parallelize some GaN transistors. As I said before, we have used 3 branches of GaN in parallel to withstand higher currents. Or we can also use adaptive modulations and work only with these GaN transistors when the power of the electrical truck in this case is low and the GaN can work with it. So talking with more detail about the gate driver. This is in our experience, some tips, some tricks to design a gate driver circuit that works with GaN. It's applicable for GaN, but also for the silicon carbide and for other kind of transistors, but it's especially critical for the GaN transistors. So first of all, we need to ensure that the input signals, the modulation signals, arrive without noise to the gate transistor, to the driver. So one method to do this is to use differential input there are some drivers in the market that they have two inputs, a negative logic input and a positive logic input. So we can use both inputs, because if there is noise in one of these on these signals, the transistors won't turn on. So with this, we can avoid short circuits. There are other methods we can use optical fiber to send the signals. We can use differential signals, but only one input, one of the driver, and so on. But this method from here is that what we are using, and in several designs, they have we have obtained good results. Another important thing is the isolation. In a power circuit board, it should be galvanic isolation. It should be isolation between the different power parts of the PCB, of the power converter. So it's very, very important to use gate drivers with isolation, with galvanic isolation between the primary side and the secondary side. And another important thing is the gate clamp. To turn on the GAN, we can do it in two ways. We can use positive voltage to turn on the GAN, and to turn off the GAN, we can use negative voltage or a 0 voltage. Depending on the application, it's preferable. It's better to use one or another. In our case, we prefer to work with gate clamps. Gate clamp is a functionality that some driver has, which is that when the transistor is turned off, there is an internal transistor within the driver, which clamps the gate voltage to 0. So if there is this effect, this gate clamp function, what it does is to reduce the voltage spike, the amplitude of the voltage spikes. So if there is a voltage spike at the output, it will be lower, and the GAN transistor won't turn on for do this voltage spike. There are also another ways to design this gate driver circuit. We can use control push train to soften the transition between the turn off and the turn off, and we can also tune the gate resistance, and we can even add some capacitor before the gate, just to achieve the same effect that with this clamp, to reduce the voltage spikes and so on. But these methods, the resistance method and the capacitors method, have an impact on the efficiency of the power converter. So in our opinion, use a gate clamp, a driver with a gate clamp is a very good solution. Let's talk a little bit about the PCB design. It's really important to design well the PCB when working with GAN, because as I said before, the GAN it's extremely sensible to the voltage spike, so we have to try to minimize the current loops on the PCB. So how to do that? First of all, putting the coupling transistors near the coupling capacitors near to the transistors, and also the gate driver near to the transistors. With these ways, we make shorter current paths, and the parasitic inductance is less than if we have the capacitors far away from the GAN transistors. We have to isolate the different parts of the PCB. As I said before, we can use the isolate drivers. And one of the main things with we use GAN is to reduce the power current loop, and also the gate driver current loop. The current loop, it's like an inductance and produce EMIs, so the interference, electromagnetic interference. So we have to reduce this path. We have here in the screen the equation for the parasitic inductance in some cases, in transistors, in some PCBs, that where the current loop returns for an internal layer, and with the power plane is in a superior layer, or vice versa. And in red there is marked an additional firm for the just for really smooth loops. But if we see the equation, we can see that the height and the length of this path of this path has a really high impact on the parasitic inductance. So it's vital to reduce these current loops. So how to do that? We have here a drawing of a PCB, and we can see that the optimum design, the pole plane and the ground plane should be near, should be near, totally close. So, for instance, if we have the pole plane at the top layer and we have an internal layer, a second internal layer, the ground plane should be this internal layer. Okay, the closest layer to the power plane. It's the same for the signals. It doesn't matter the order. It doesn't matter if the ground plane is the top layer and the power plane is the adjacent layer, but it should be using this kind of design to minimize the current loop. And on the PCBs, here we have a picture of a real PCB that we have here on the lab. There is a picture taken with a microscope, and we can see that the layers of the PCB goes in groups of 2. This is called orthogonal layers in some literature. So we have a PCB of 4 layers. We will have a layer of a layer, a little bit of isolation material, another layer, a really high part of isolation material, and then other 2 layers. Okay, the layers always comes in group of 2, and the distance between these groups of layers is really significant. We can see here on the picture, we can see the top layer and also the internal layer. Then we have a really high part of isolation material, and then the other 2 layers. So it's really important that the ground plane, the pole plane and the ground plane we will design the PCBs using these groups of 2. Okay, we cannot put the pole plane on the top part of the PCB and then the ground plane on the opposite side of the PCB. We have always to use the closest layers because they really minimize the parasitic inductance. I think that depends on the manufacturer, but between the top layer and the internal and the first internal plane, there is a separation of micras, and between the 2 internal planes, we have a separation of millis. So in perspective, as we can see here on the microscope, is there is a significant difference. So this is really important. It's one of the most important parts when designing PCBs using GaN transistors. So let's finish the presentation now, just showing you some results of our experimental prototype and so on. We have designed this prototype. This is a low power prototype. This is not intended to work with electrical track. The power converter which will go with electrical track is developed in the Austrian Institute of Technology. Is based on this design, but of course the geometry is different and so on, but the core of the design is the same. So here we only have 2 GaNs to connect connected to the midpoint of the DC bus converters. So here we have the components and so on, and we have the drivers that we used on the design. These drivers followed all the guidelines that I said before, and I think that the most important part of this design is that we use a modular design. We have a motherboard, which is just a board connected to the supplies. When in this board we connect the rest of the boards, so we can manufacture another motherboards with more slots, and we can easily expand the power converter and have a 5-phase converter, a 7-phase converter, or whatever what we need. just modifying this PCB. And we have also power boards, control boards. The power boards is where the transistors are, and the control boards is where the signals and the sensors arrive. So we have one for each phase. In this case is a 3-phase converter. For each phase, we have the power board with their control board. This allows us to replace one of these boards if there is a failure during the operation, or if there is an explosion. For instance, let's imagine that we are driving a truck. There is a problem with the power converter, or one of the phases explodes. So we can just replace the PCB and continue the operation, and the old PCB or the destroyed PCB, we can send it to the manufacturer to fix them. But we can easily continue the operation with this kind of modular design. And here we have, just to finish, some experimental results. These results we presented these results in a congress the last month. And we tested the power converter at different frequencies to see what happens. We have seen some values of efficiency. They are really high. They are higher than 97% at high powers, a high modulation index. We have also values of total harmonic distortion, and we have also values about the common mode voltage, which can also be improved if we use more advanced modulation than the one applied. I think that an important thing here is to highlight how an increase in the switching frequency does not negatively affects to the power converter. I mean, the higher the switching frequency, the lower the efficiency, the higher the electromagnetic interference. But in these results, we are doubling the switching frequency, and the impact is not as significant than the impact that will be if we will use a full SiC-based converter, or of course a full silicon-based converter. So the GaN transistors here are doing their job, and they are not really using these GaN transistors has no negative effects when we use higher switching frequencies. And another thing here is there is an image. You can read voltage in blue and current in red at the bottom part of the slide. And here there is the operation of the power converter. And the first part of these waveforms, the power converter is using all the transistors, and we have a multi-level voltage at the output. In fact, a three-level output. We can see here more levels because this image is from the voltage in this image is the voltage between the phase A and the phase B. So, but the point is that, and more or less at the 5 milliseconds, we change the operation mode, and we only operate with the GaN transistors, with the SiC transistors, sorry. And this is the behavior that they said at the beginning of the presentation. This kind of power converter allow us to disconnect the GaN transistors, in this case, the transistors that are connected to the midpoint of the DC bus, and operate only with the SiC transistors, like a standard 2-level converter. And this is really useful when we have a failure on the GaN transistors, or when we want to operate with high output powers, because we can just disconnect the GaN transistors and use the SiC transistors and continue the operation. So this T-type topology is very useful for that. So that's all on this presentation. Here we have some frequently asked questions, but we will upload the presentation to the RHODaS website and to the other website, so you can read with more calm these questions. And that's all for my part. So thank you very much for listening. And now Sergio Busquets, also from the UPC, Dr. Sergio Busquets, will present the presentation. And then after this presentation, we will have a short Q&A session. So thank you, everyone. Now, Sergio, you can present.
Yeah. Can you hear me? Sorry.
Yes.
Okay. I wasn't sure if my audio was activated. Well, thank you very much for inviting me to present in this webinar the SCAPE modular and scalable EV power conversion architecture. SCAPE project has been going on for 3 years now, more or less. So I will be glad to share with you our progress and our approach. So the outline of the presentation is as follows. We will first quickly have an overview of our design approach for power converters in the electric vehicle. And then we will go through the details of the different hierarchical modules that we have defined, the switching cell, the converter leg, and the full converter. And finally, we will have some remarks at the end. Let's start with the overview. Let me start with some definitions. We are targeting a modular and scalable design approach. What is a module, or what is a modular and scalable system? A module basically is an independent unit, okay? So we understand that a modular system is a system constructed, built with a combination of modules. This brings some interesting advantages. First of all, we can take advantage of economies of scale because these modules can be reused in different equipment, or they can even, several instances of the same module can be used to build a given equipment. So this, in the end, provides some advantages from the economies of scale point of view. Also, the modular system always have a better configuration flexibility because we can change the features of the system, of the equipment, by simply changing one of its modules, rather than redesigning the whole thing. And also, it fosters circularity in the design. It makes it easy to reuse, repair, refurbish, and recycle these modules, and then have a better impact on the environment. Okay, so all this regarding modularity. What about scalability? What is a scalable system? Well, a scalable system is a system that is easily expanded or upgraded. In the context of power electronics or electrical systems, this means that the voltage and current rating of the system can be easily adjusted, and therefore also the power level of the system. So a modular power converter will be scalable if multiple instances of the module that forms the converter can be properly interconnected to produce any desired voltage and current rating. So basically, we target power converter designs where we have a module that we will replicate many times, and we will interconnect them in a way so that we can reach different voltage and current ratings. So with this, let me move to see what is the system we are targeting in SCAPE. We are targeting the main power conversion systems inside an electric vehicle. On one hand, we have the high voltage traction battery. On the other hand, we have the low voltage service battery. And then we have a traction inverter connecting the high voltage battery to the motors, the motor or the motors. We consider the full integration of the onboard charger within the traction inverter to minimize the space required by power conversion systems. And then we also have a DC to DC converter interfacing the high voltage traction battery with the low voltage service battery. In SCAPE, we aim to design all these systems in a modular way. We will define a basic module in the converters that we call the switching cell that we will use to produce these converters. But also we extend the modularity to the batteries also. we define a battery module to build the high voltage traction battery, and also another battery module to build the low voltage service battery. In SCAPE, we have fixed the high voltage battery module to have a nominal voltage of 400 volts, while the low voltage service battery module, the low voltage battery module, has a rating around 12, well, a nominal voltage of 12 volts. Then, in connection with the high voltage battery module, we have the high voltage switching cell, which is rated at around 600 volts. And in connection with the low voltage battery module, we have the low voltage switching cell, which is rated at 30 volts approx. Okay. Well, said this, let me just present our approach, and I will start by explaining that we develop converters following a hierarchical modular approach. At the lowest level, we have what we call the switching cell, which is basically a power switch that is complemented by a self-power intelligent driving, monitoring, and protection circuitry. Essentially, the switching cell functions as an ideal switch with an anti-parallel diode, okay? And then we combine the switching cells to form the next level module, which is the converter leg, the higher level module, which is the converter leg. These converter legs will behave as a single pole multiple throw switch. So essentially, we have a commutator that connects the AC terminal to one of the DC link points. And then finally, these converter legs can be also combined to produce the highest level module, which is the full converter. Okay, in this example, we have been using three level legs to produce a three-phase motor drive for an electric vehicle, for example. That is controlling the energy flow from the battery bank to the motor. This modularity in the hardware design is also applied to the controller design. So we have three types of controllers: the primary control at the switching cell level, the secondary control at the converter leg level, and the tertiary control at the full converter level. So the system behaves as follows. From the highest level controller, which will be here, we receive the information on the full converter state, which essentially is the information on the state of health and the stress that this converter is suffering. And based on this, we can decide which command to send to the full converter, to the tertiary control. This command could be, for instance, the torque to be applied to the motor. And then the tertiary control, taking into account the converter leg states, translates this command through some closed loop control and modulation into the converter leg commands. These converter leg commands basically represent the position of the leg, whether it is the AC terminal is connected to DC1, DC2, or DC3. So it is telling the converter legs to which DC link point the AC terminal should be connected. Then the secondary control, taking into account the state of all switching cells, the state of health and the stress of all switching cells, will translate this converter leg command into the command to turn on or off for each switching cell. And that's basically the hierarchical approach applied also to the control. So in the end, from the control point of view, as you can see, we have a bunch of controllers at different levels, which are interconnected in a tree structure with bidirectional information flow. This design approach is easily scalable as follows. To adjust the voltage rating, the only thing we need to do is to adjust the number of levels of the converter legs. by increasing the number of levels, we increase the voltage rating. And the current rating can also be adjusted by paralleling some switching cells. So for example, in the two-level leg case, if we, instead of one switching cell per position, we put two in parallel, we will increase the current rating, and similarly, we can increase the paralleling to increase the current rating. In the multi-level MPC type, active MPC type structure that we use for these converters, basically the paralleling to increase the current rating takes place essentially in the outer diagonals of these legs. So in SCAPE, we have decided to study this design approach in a simplified scenario where we have to target the design of three simple vehicles, one motorcycle, one car, and one truck. The motorcycle motor power is set to 50 kilowatts, the car power at around 100 kilowatts, and the truck at 300 kilowatts. The battery interfacing converter has to handle half kilowatt for the motorcycle, 1 kilowatt for the car, and 3 kilowatts for the truck. This should be nominal values. In any case, the idea is to come up with a design for these three vehicles with using only two battery modules, as discussed before, and two switching cells, as discussed before, the high voltage switching cell and the low voltage switching cell. So let's now get inside these different modules, and we will start with the switching cell. Here we have a simplified schematic of the switching cell, where we show that this switching cell, essentially in the power part, it has a power device, a power switch. In our case, we are using for the high voltage switching cell a silicon carbide MOSFET, and for the low voltage switching cell a gallium nitride HEMT. And this can be complemented in series with another power device, which we call the iFuse. And the mission, this is an optional device that you can add. And the idea is that this device will help isolate in open circuit the switching cell in case of if there is a fault. Okay, so essentially this device is on all the time and only turns off when there is a problem with the switching cell to isolate it and let the system continue the operation without too many issues. Then we will have a driver for, and also we have, typically we can also include a shunt to measure the current. Although we can also use this device as a shunt for measuring the current, since it is permanently on. Then we will have the driver circuits for both devices and the power supplies that, as we mentioned before, this is a self-power supply. So essentially the energy that we need to power the switching cell is taken from the voltage across the switching cell and the current flowing through it. Ideally, we take the current in the turn-off process, recycling switching losses to power the whole circuit. And if not, we then take the energy from the capacitor that is connected across the switching cell when it is off. But in any case, then besides the driver circuits and the power supplies, we also have some sensing circuitry. In the designs we have been developing in SCAPE, we are measuring temperature, current, and voltage, the three things, three main things in the switching cell. And then we have some digital processing circuitry that essentially takes these measurements and determines whether the switching cell is healthy or not. And if there is a failure detected in the switching cell, it will turn off the iFuse so that the whole system can continue operating without too many problems. And then we have some connectors to provide the interfacing for the signals that the primary control is exchanging with the secondary control. In this slide, I'm showing some pictures of the switching cells that we have developed in SCAPE. On the left, you have the high voltage switching cell using 650 volt silicon carbide MOSFETs. On the right, you have the low voltage switching cells using 40-volt gallium nitride HEMS. Let me focus now on the high voltage switching cell. Here you have the top and the bottom images of this switching cell. As you can see from this picture here, the power components, the power switch is embedded into the PCB. We are using chip embedding to introduce the MOSFET devices inside the PCB. Also, the current shunt is embedded into the PCB. This is bringing us important advantages regarding thermal resistance and leakage parasitic inductance. So we are reducing a lot these parameters. Essentially, the chip, the bare die, is located inside a copper frame, and this copper frame is then is put inside the PCB during the PCB production. Then we have already some embedded isolation of the chip inside the PCB, and then everything is connected to the bottom copper plane that can be directly attached to the heatsink. And you can see a picture of the switching cell attached to the heatsink. So this chip embedding, I think it's enabling important advantages regarding thermal and electrical performance. And then here on the right, you can see a picture of the low voltage switching cell, which has been developed around a gallium nitride device, a 40-volt gallium nitride transistor. And we have also integrated all the logic circuitry into one chip. Then let me move now to the converter leg. One of the important things at the converter leg level, from the hardware point of view, is to decide how many switching cells and how they will be interconnected to produce these converter legs. You can here see the optimal design that we have come up with for the three vehicles. For the motorcycle, we are using a two-level leg with 4 switching cells. For the car, we are using a 3-level leg with 8 switching cells. In fact, the true optimal design was having 2 additional switching cells here in parallel with these 2. But to reduce the complexity of the control and the design, we decided to go with this 8 switching cell design, which is fairly close to the optimal. And then for the track, we have a 4-level converter leg with 24 switching cells. It's interesting to note that the number of switching cells that we have been using follows the proportion of the power level. So the power was 50, 100, 300, and the switching cells also follow this proportion, 1 to 6, okay? So it's kind of interesting to see that this modularity ends up translating into a proportional number of switching cells. Then another important thing at the converter leg level is that this design approach enables 2 interesting degrees of freedom, which relate to the control, the distribution of the conduction loss within the leg among the switching cells, and the distribution of the switching loss. So we have degrees of freedom to play with the conduction and switching loss and distribute it in different ways among the switching cells. Regarding the distribution of the conduction loss, you can see clearly how this works with this example. We are taking the example of the converter leg for the traction inverter of the car. And here in the connection of the AC terminal to DC point 1, you can see that we have 3 possible connections along the switching cells. In fact, the idea is that between the AC terminal and the DC link terminals, we may have more than one possible path, which is what happens here. We have this path and we have this path. And then we can either enable one of the 2 paths, or we can enable both at the same time for minimum conduction loss. And this will determine different conduction loss distribution among the switching cells. Similarly, for the connection to DC point 2, where we have the bottom path and the top path, and we have the option of enabling both. And the connection to DC link point 3 is analogous to the case of DC1. So we can play with these options to distribute conduction loss in different ways. In addition, we have also degrees of freedom to distribute the switching loss. In the transition from the connection to one DC link point to another DC link point, we'll have to turn on and off several switching cells. In this case, for example, in the transition from DC1 to DC2, we need to change the state of these two switching cells and these two, a total of 4 switching cells. Depending on the current direction, the switching losses will be concentrated on these two switches, in one of these two switching cells or in one of these two. Here you have the negative converter leg current case, and here the positive. In the negative case, the switching losses are concentrated in one of these two switching cells. And we can select which switching cell takes the switching loss by simply rearranging the stages of the switching transition. Essentially, the switching cell that turns on first or turns off last will be the one taking the switching loss. So for example, in the top row, we have selected this switching cell to take the switching losses in both transitions from DC1 to DC2 and the opposite. And in the bottom row, we have selected this switching cell, the right one, to take the switching loss. And this is just by simply rearranging the transitions during the switching transitions of the converter leg. Here you can see a picture of the detail of the signals that the different controllers are exchanging. Okay, this is the solution we have developed in SCAPE, which is a simple solution that takes into account several functionalities, but obviously it can also be expanded to take into account more things. I will not go into the details of the signals, but just to let you know more or less the amount of information exchange between controllers. This obviously requires a good synchronization of all these communications and so on. Let me show you now some prototypes of the traction inverter converter legs that we have developed in SCAPE. This on the left, you can see a mock-up prototype where we have integrated the switching cells into the PCB. In this case, we are using discrete components as the main power switches. And as you can see, well, this design was targeting full integration. But obviously, if you have an issue with one of the switching cells, you cannot replace it, okay? So on the right, you can see another option, which is what we are targeting for the final demonstrator, which is a converter leg using detachable switching cells that are using, in this case, chip embedding. We are using the switching cells with chip embedding in this case. And the nice thing here is that if a switching cell fails, we can easily replace it by a new one without having to modify the rest of the board. Obviously, there is a challenge in this converter leg design, which is minimizing the parasitic inductance, as has been discussed in the previous presentation. And for this, we have been developing our own method to provide a low parasitic inductance design. Let me finally move to the full converter. In the case of the integrated inverter charger, we have developed a topology around a 6-phase symmetrical open winding machine. This is a machine that enables an easy design for this fully integrated traction inverter charger. And the idea is that for the power converter, we are using a 6-phase multi-level MPC DC to AC converter. You can see here that in the motorbike case, we are using a 2-level converter. Here for the car, we are using a 3-level, and for the truck, we are using a 4-level. And the idea is that through a reconfiguration of the connections of the open-end windings, we can either make the system operate in traction mode with 1 neutral, with 2 neutrals, or we can charge the battery in single phase or 3-phase. This requires reconfiguring the connection of the open-end windings, but also you can fix these connections at the expense of losing some functionality. Then for the battery interfacing converter, we have been using a dual active reach, a multi-level MPC dual active reach. For the motorbike, we have 2-level legs, a single phase transformer, 2-level legs on the high voltage battery side, a single phase transformer, and 2-level legs on the low voltage battery side. For the car case, we have 2-level legs on the high voltage battery side again, but 3-level legs on the low voltage battery side, which enables the powering of loads with 12 volts and 24 volts. And then finally, in the truck case, we are using 3-level legs on the low voltage battery side to be able to power loads with 12, 24, and 36 volts. The project demonstrator focuses on the car use case. And here you can see the system we are working on implementing for the final demonstrator. Here you can see the integrated inverter charger with a 3-level 6-phase design. And then here you can see the battery interfacing converter and the optimal leg configuration for the different legs in the converter. The traction inverter is, the switching frequency for the traction inverter is targeted at 50 kilohertz, while the switching frequency for the bottom converter, the battery interfacing converter, is around 100 kilohertz. And we have been developing closed-loop controls and modulations for these systems. This is the case of integrated inverter charging. In integrated inverter charger, we have a closed-loop control that regulates the power flow between the battery and the motor, and another closed-loop control that regulates the balance between the state of charge of the 2 battery modules. And then we use a virtual vector-based pulse width modulator that enables the control of the neutral point current in every switching cycle. And we have also been developing advanced modulation and controls to assess and eventually manage the battery, converter, and motor state of health. Regarding the battery interfacing converter, you can here see the relevant waveforms. The voltage at the high voltage battery side is basically a 2-level waveform. And the voltage at the low voltage battery side, since we are using 2 legs, 2 3-level legs, we have a 5-level voltage. The relevant modulation parameters are the angle alpha and angle phi. And these parameters are defined by a closed-loop control that takes as inputs the average value of the state of charge of the battery modules and the difference in this state of charge of the battery modules. And finally, as a conclusion, let me mention that so far, from our experience, we can say that the advantages of the proposed modular and scalable design approach are that it enables the taking advantage of economies of scale, reaching higher efficiency, reaching lower harmonic distortion compared to 2-level systems. And overall, this leads to higher power density. We also have a tight control of the battery and the motor. For example, we can regulate the state of charge of the battery modules without the need to introduce lossy elements in the battery management system for this. And we also can reach higher reliability because the system is fault tolerant. And also, we can easy the reparability by having detachable switching cells and converter legs. There are still some challenges, though, obviously. One of them is that the design is complex, okay? And this is why we are working and doing research on this to simplify as much as possible this design and come up with design rules that make it simple. And also the control complexity is higher because we have many more switches operating at the same time. So obviously this is also a challenge. And this is all from my side. Thank you for your attention. I hope I didn't went too far with the time.
Thank you very much, Sergio. So let's start the Q&A sessions. I don't know. I would say that if there are some questions first, let's make the questions for Sergio for the SCAPE project. Since Sergio has to leave, so I don't know if there are some questions. Okay, for Sergio, there is a question for you. It is, what impact in performance have you observed using chip embedding as compared to using standard discrete components or power modules?
Yeah, okay, thank you. Well, in fact, I believe we will explain the detailed results in the next webinar next week. But I can say from what I remember that in the testing we have done, we have reached a reduction on the thermal resistance junction to case above 50%. So the thermal resistance from junction to case is lower than half what we typically have for a discrete component or a power module. So this is a very important result. And also regarding the parasitic inductance, we also, I don't remember the numbers, but I think we reach a substantial reduction higher than 50%. I think the final parasitic inductance was of the switching cell itself was around 1 or 2 nanohenries, which is quite low. And then we are also very happy with these results too. But I guess Xavier Jordan next week will provide more details on this topic.
Okay, we have more questions for the moment, just for the RHODaS project. I don't know if there is just a few questions more for Sergio, since he has to leave. So Sergio, they said me that very interesting your answer. So thank you very much.
Okay, thank you very much.
I don't know if we have time for more questions for you, Sergio.
Yeah, well, I can stay a couple of minutes more, maybe. But if there are no questions,
okay,
you're the stage for your.
Okay. Now, for the moment, just that there are some questions for the RHODaS project. So.
Okay. So maybe.
Yeah. So maybe you can leave.
Yeah, well, okay. That is perfect because I have to teach now. Okay.
Thank you very much, Sergio. So thank you for your teaching us for performing this webinar. So have a nice day. We will see on the next webinars.
You too, my pleasure. Bye bye.
Thank you very much. So let's continue with the questions. Since Sergio has to leave. We have 2 more questions, in this case for the RHODaS project. First of all, there is one question, which is how do you expect the hybrid wide bandgap converter architecture to influence future heavy-duty electrical vehicles powertrain designs? And what do you see as the biggest barrier to scaling this technology to mass production? The main problem with here is as I said on the presentation, in my opinion, is the GaN transistors. The GaN transistors are really it's really difficult to make commercial designs with GaN transistors. There are some designs, but not for high voltages or high powers. So there are, and especially the part the gate driver circuit design. So there are some manufacturers now that are manufacturing the GaN devices with the integrated driver, with I hope that will make easier the future designs of commercial power converters. And this is the first step. And the other steps are the power modules. We have no power modules using GaN transistors, so of course we will not have hybrid power modules. So that's the main problem, that there are some scientists which are working on these topics, but for now we only have discrete GaN devices, and just a small part of these devices have the driver integrated. So I think that the other question, which was about the influence of these hybrid power converters on the heavy duty powertrain designs. I don't know about the hybrid, as I said before. I think that there are some barriers now, but about the wide bandgap power converters on the electric mobility, these are reality now. Some manufacturers are performing, are just commercializing trucks, commercializing cars with especially with silicon carbide power converters. They show great efficiencies. There are more smaller and lighter than the traditional silicon converter. So these technologies will allow us to have more efficient electrical vehicles, especially. And the next step is using multi-level topologies. We have now in the market, we have the two-level silicon carbide converters, but the next step is having the multi-level topologies, especially T-type converters, to their advantage, since we can manufacture these T-type converters, these modular T-type converters that are more, they have some fault tolerance. So we can operate also with two levels if we want, etc., etc. They have a very interesting properties that I think they are expensive, more expensive than the two-level power converters, but they have some advantages: less losses, less interference, electromagnetic interference, and so on. So we can extend the lifetime of the electrical motor and so on using this kind of technology. And okay, we have another question also for the RHODaS project. Then yes, it's the following. Have you considered the use of 650 voltage rate SiC MOSFET instead of the GaN transistors? They show similar electrical characteristics and the TO247 package, which is easier to cool. Thank you. Yes, that was this is a possible solution, but and a very interesting question. But and the thing is that the transistors that are connected to the midpoint of the DC bus withstand only half of the DC bus voltage. So it makes no sense to use the same transistors for all the T-type. We can optimize using transistors with lower, that can withstand lower voltage at this on these positions. So yeah, using SiC transistors will be a solution. However, since we are talking about silicon carbide, the performance of these transistors will be worse than the GaN transistors, but the design will be easier because they are easier it's easier to extract the heat from these transistors, and the gate driver design is easier also. So yeah, it may be an interesting alternative. But there is another alternative, which is using T-type modules. Some manufacturers manufacture already commercialized full SiC T-type modules. So we have to check the voltage, the rated voltage, the power rating, and so on. But a more simple solution will be using these T-type modules, which will simplify a lot the design of the pole converter. I don't know if there are more questions. Okay. If there are no questions, I think that we can close this webinar. So thank you everyone for attending this webinar series. It has been a pleasure to present the advancements on the RHODaS project and also on the SCAPE project. And see you the next week on the second webinar of this series. Thank you very much.